Welcome you to this series of lectures on marine hydrodynamics, and in the last lecture we were talking about various solution methods or to deal with the bounded layer flow problems. And in fact, the two methods we are emphasizing out of the three, one is the finite difference method, but our emphasis, we have given emphasis just to two methods, that is self similarity method and then the momentum integral method. So, and we have derived the momentum integral method, the general form of the momentum integral method for two dimensional boundary layer flow when the motion is steady, and the equation says that is del by del x delta 2 u naught square plus delta 1 u naught du naught by dx, this is equal to tau naught by rho. This is what we have derived in the last class. Delta 1 u naught is equal to 0 to infinity u naught minus u dy, and that is nothing but 0 to h u naught minus u dy. Similarly, delta 2 u naught square is nothing but 0 to infinity u into u naught minus u dy, which is same as, because beyond the boundary layer the stream velocity is same as the fluid velocity, this is 0 to h. So, this is u into u naught minus u dy. So, this was basically the momentum integral method, and one of the advantage of this method is that this method is suitable to not only to deal with boundary layer flow equation, laminar boundary layer flow problems, but also it can be dealt with help in understanding or getting the solution for turbulent flow problems. This is that is a more general and one of the robust method, and which is called the momentum integral equation method. This method can be further generalized to deal with when the motion is unsteady. The same method with a unsteady contribution will also be there, and also it will be one of the most general approach to deal with this both laminar and turbulent flow problems. Now, today we will discuss only from this only we will go to look into approximate solution. This is the general form of the solution of the equation, but how to get a solution. So, let us look into approximate solution for the momentum integral equation. Approximate solution methods. So, there are many ways we can do that. So, one of the things that let us write, assume on the case 1 will go to. In this case, we will assume that suppose u naught x t is u naught. So, basically we are going to look into the glacier solution, the same problem, semi infinite flat plate when there is a pressure gradient is 0. So, this is constant. If I say this is constant, this is same as dp by dx is 0, because u naught du naught by dx will be constant, it will be 0. So, dp by dx will be 0, and sometimes we call this problem as a flow past a rather we call it flow over a flat plate with 0 pressure gradient. So, basically here the flow is, I mean the boundary layer flow, other call it boundary layer flow over a flat plate with 0 pressure gradient. So, if this is the case, then what will happen to our the boundary conditions? So, in this case, because the dp by dx is 0, u naught is 0. So, what will happen here? U naught will be 0 here and du naught by dx will be 0. So, the momentum integral method equation will be reduced to del by del x. It will be further simplified. It will become del by del x del 2 u naught square is equal to tau naught by rho. This becomes my equation of momentum integral equation. And what are the boundary conditions? The boundary condition will be, now to deal with what I will do, I will go for a linear approximation based on a linear approximation, the solution of this. If I look into the linear approximation, then what will happen? I will just calculate my u by u naught, I will say that this is f of eta and that is a0 plus a1 eta, where eta is nothing but y by delta. Delta is a boundary layer. It can be a function of x. So, if this is the case, then what will happen? Because if I look into the, I have y is equal to 0, u is equal to 0 and y is equal to delta, u is equal to u naught, because beyond y is greater than equal to delta, u is equal to u naught. So, if I take this into account, then that will give me, which implies f of eta, and further I say f of eta is u by u naught already. So, if f of eta is u by u naught, then f of eta is my u by u naught. Okay. So, f of eta, this is 1 and f of eta is u by u naught, which implies my y is 0, u is 0, at y is equal to 0, u is equal to 0. So, that gives me f of 0 is 0 and further y is equal to delta, u is equal to u naught, that gives me f of 1 is equal to 1, because beyond y is equal to delta, that is y is equal to delta, y is equal to delta means eta will be y by delta, eta is y by delta is 1. So, in the process when eta is equal to 1, then u by u naught becomes 1. So, this gives me this. So, this becomes the two boundary conditions and my f eta is a0. So, I have two unknowns and two boundary conditions. So, if I substitute for f0 and f1 in this expression approximate solution, I call this as an approximate solution, then I will get my f eta as eta, f eta as eta. So, this will be just from this using this and this. So, this becomes f eta is eta. If f eta is eta, then what will happen? My u by, so that means u by u naught becomes eta, where eta is equal to y by delta. Now I will substitute for this u by u naught eta in the original equation, that is my star equation. So, if I do that, then that will give me del 2 so if I substitute for this del 2 u infinity, so that will give me del 2 u infinity or del 2 u naught square, and that will be nothing but 0 to 1 u into u naught minus u dy, and this is what del 2 u infinity square, if this is the, then which implies, now I will substitute for, I have del by del x del 2 u and del 2 infinity is, this becomes 0 to 1. If I call it del 2, then this becomes u by u naught into 1 minus u by u naught into dy. Now del 2 becomes this, and if del 2 is this, so which gives me in terms of delta. So, del 2 will give me delta times 0 to 1 eta into 1 minus eta deta, and which is nothing but delta by 6. So, del 2 is a delta by 6. Now, I substitute this same into the equation of integral equation in a similar manner. So, what I will get if from star, is I call it 2 star, from star and double star, I will get u naught square d del 2 by dx into tau naught by rho, and which gives me d del, because del 2 is del by 6. So, I will have u naught square by 6 into d del by dx is equal to tau naught by rho. But what is tau naught by rho? Now, if I look at tau naught by rho, this is nu into del u by del y at y is equal to 0, and that is nothing but nu into u infinity by delta, because I have u is equal to u infinity eta, and that means what will happen, del u by del y, that will give me del u by del eta into del eta by del y, and del u by del eta, this is u infinity or u naught, I am taking at u naught, del eta by del y is eta is y by delta. So, that will give me del by del y by delta, and that gives me u naught by delta. So, this becomes, so that is why, so nu into u naught by u infinity, sorry, that I am taking as u naught. So, this becomes u naught by delta, that is one. So, what I got tau naught by rho is this. So, I substitute for this. So, that will give me u naught square by 6 into d delta by del x dx is tau naught is nu by rho into u naught by delta. So, that gives me, which implies d delta by dx is equal to 6 by rho, this is u naught square rho tau naught, because tau naught tau naught is u naught delta. Okay. So, now if I substitute for tau naught in terms of nu u naught by delta, then I will get it. I substitute for this, I call it 3 star from 4 star. So, from 3 star and 4 star, I will get delta into d delta by dx, that will give me 6 nu by u naught, and that gives me delta is equal to 12, delta square is equal to, because that will be delta square into 12 nu x by u naught, and that means my delta becomes 12 root over into 1 by Rex, because where Rex I am taking u naught by nu x. Okay. So, this becomes, and then if delta is this, then delta 2 is delta by 6, that is 12 by root over by 6 into 1 by r e x, and that is root over, that becomes 0.577 into call what we called nu x by u naught. This is my delta 2, and in a similar manner if I look at delta 1, I will see easily that it is nothing but delta by 2, and it will be 1.732 into nu x by u naught, and in the process tau naught x, that is the wall shear stress. One can easily find that this is mu u naught by 3.464 into u naught by nu x. This will be my wall shear stress. So, this is a, so what we have got? We have got delta, we have got del 2, we have got del 1, and we have got tau naught x. So, we can always find the screen friction coefficient and other factors associated with it. Basically, if we want to find the drag coefficient, then we can easily find it because we know tau x, and we know all these parameters because from various displacement. So, this is the way, this is one of the way what we have got, that how we can solve the momentum integral equation. There are, we can start with the several other cases we can also consider to find the final solution of the momentum integral equation. Like instead of considering f of eta as u naught by u, sorry, u by u naught, and that we have taken a 0 plus a 1 eta, that is a linear approximation. We can also think of a approximation like f of eta, I can always take as a 0 plus a 1 eta plus a 2 eta square, or I can think of another approximation like it is a quadratic approximation. I can think of also a cubic approximation. I can also think of other approximations like exponential approximation 1 minus e to the minus alpha x into y. This is a exponential, this is a cubic approximation, and this is a exponential. Then we can also go for a trigonometric approximation. The various approximation, of course, all depends on, there will be error, but that depends on the nature of the problem, and these approximations where the details I will not go to that, but in case of another sinusoidal approximation, that is sin pi eta by 2, 0 less than equal to eta is less than equal to 1. This is called a trigonometric approximation. And many more many such approximations. There is another approximation called Paul-Hausen approximation. This is I am not, it is a kind of again it is a kind of a polynomial approximation. It is a kind of polynomial approximation. Rather I will call a special type, a special type polynomial approximation. This can be found in various textbook, and so out of these approximation we can also find what is eta, and once we know f of eta, that means we know u by u naught the velocity profile, and then we can find the wall shear stress and other physical quantities of interest. So, I will just give in a brief, suppose I have a cubic, sorry, I have a quadratic one, then what I am doing, what additional thing, because my problem is fixed, how I am going for this. So, in the case of a quadratic approximation, so as I said that I will take u by for a quadratic approximation, just I will state the intermediate steps how I go for this, particularly how I am adjusting the boundary condition. So, I have been given u by u naught is equal to f of eta is a 0 plus a 1 eta plus a 2 eta square. So, in this case what I do, I have the boundary condition because I am have the same semi infinite plate. So, y is 0 and u is equal to 0, and that gives me f of 0 is 0 and y tends to infinity, u is equal to u naught, which implies y is equal to delta, y is equal to delta, u is equal to u naught, because beyond delta y is equal to, it is same as the behavior at infinity. So, that gives me f of 1 is equal to 1. Then I have another one, as y tends to infinity, del u by del y also will tend to 0, it can be, because as y tends to infinity u becomes u naught. So, I will, and it is a function of x. So, I can also say that y tends to infinity, del u by del y tends to 0, and that implies same as y is equal to delta u del u by del y will 0, and which gives me f dash 0 f dash 1 equal to 0. So, earlier I had, when I was going for a linear approximation, I used to take two terms and these were my boundary condition. Now, when we are going for a quadratic approximation, I am adding this condition. So, that is, there is no harm in adding this condition, and in the process I am getting a better approximation. If I go with that, then I will find out, because I have now 3 conditions, 1, 2 and 3 conditions for on eta, and this is my f of eta. So, I can easily find a 0, a 1 and a 2. So, what I will, if I take substitute for these conditions in this expression for the polynomial f eta, then I will get my u by u naught is equal to 2 eta minus eta square. This will be the approximation I will get. This is my quadratic approximation, and in this case eta is equal to y by delta. So, then again now I substitute for this in the momentum equation. If I substitute this in the momentum equation, I will get my del 2 is equal to y is equal to 0 to infinity u by u naught 1 minus u by u naught dy, and that will give me delta times 0 to delta f into 1 minus f of eta deta, and this gives me nothing but 2 by 15 delta. So, delta 2 becomes 2 by 15 delta. You can just see that in the earlier case, in case of k1, when I had a relation, then I had seen that my delta 2 was 1 by 6 delta by 6. In the earlier case, when I have a linear approximation, my delta 2 was delta by 6 in case of linear approximation. Delta by 6 linear approximation. On the other hand, we have delta 2 is 2 by 15 into delta in this case of quadratic approximation. In a similar manner, I can find out what exactly is happening, the momentum I will have, what will happen to my tau naught by rho, that will be nu del u by del y at y is equal to 0, and this will give me, if you calculate it, that will give me 2 nu u naught by delta, and then again if I substitute this delta 2 and tau naught by rho in the momentum equation, then I will get delta d delta by dx is 15 by u infinity into nu, and which gives me delta 2 gives me delta as 5.48 to nu x by u naught, and which implies find delta 2 is 0.7306 into nu x by u naught. This will be my delta 2, and this is my delta, the boundary layer thickness. Further, I will have tau naught x. I can always find 2 mu. Okay. So tau naught x will give me this will be 2 mu u naught by 5.48 into u naught by nu x. In case of a quadratic approximation, this is my wall shear stress, and say thus the other quantity like the drag coefficient CDD and CD can be obtained from this, because we know tau naught x. These are the can be easily obtained. So, this is the drag coefficient, and then is the drag force per the that is acting on the upper side of the plate, that will be obtained easily. So, this is the way we can apply the momentum integral equation. As I have mentioned that this momentum integral method is suitable not only for boundary layer flow problems, but also for turbulent flow problems, and in the process this becomes like on the other hand, when you look into self-similar solution, the self-similar solutions have only restricted to a simple class of problems. It is not suitable for all kinds of problems like self-similarity. This is only when we have flat plate problems, or to wedge flows. This is more suitable, self-similar solution is suitable. On the other hand, these kind of self-similar solutions are not suitable for separation flow, to analyze like separation flow, turbulent flows, your flow near suction or injection flow, suction or injection flows, or flow along a curved surface. For these self-similar solutions and are not suitable, rather the most appropriate method are in this case the power series solution method, integral method, or perturbation theory or perturbational approach. So, self-similar solution only suitable for this, but not suitable for this class of solution, and in this case we always go for the power series method, alternate methods. So, these are the methods we apply for this class of problem, which is not possible, for which the self similar solution approach will not be applicable. And here the integral method, in the process the integral method becomes one of the robust method to deal with a more general class of problem. So, with this understanding of the methods on this solution to deal with boundary layer theory, we will not go further, we will not go into the details of other flow problems associated with the boundary layer, but we have just, as I said, that we will just briefly discuss about what is boundary layer theory and the two dimensional governing equation, and then two approaches we have talked about. One is the self similar solution approach and then the momentum integral equation method, that is based on the residue method, weighted residue method, and two examples we have worked out. Particularly in both the cases, we have taken the same example to show the solution of a boundary layer flow equation by two methods, and we have seen how the solution is easily obtainable without much of a difficulty, but there are large class of problem for which solution can be easily obtained, and there is a large a series of lectures by under this NPTEL program by faculty of civil and mechanical engineering departments of IITs. So, those lectures can be looked into for further detail on various types of boundary layer flow theories. Now, I will just briefly mention, because today we are almost completing our series of lectures. So, I will have a few things to mention, that what about flow separation. Already few points to mention before I conclude this flow separation. I have already told when the pressure gradient along a body surface becomes negative, when del p by del x is equal to less than 0, the pressure acts to accelerate the flow, then the pressure acts to accelerate the flow. Along the body. And what it does, it tries to overcome the, and in the process it overcome the viscous resistance. Because viscosity will provide as a resistance. So, when the pressure acts to accelerate the flow, so it overcome this viscous resistance, a viscous force effect, and in the process, while this viscous resistance, what it does, so in the process the flow decelerate. On the other hand, what happens when the pressure becomes, when del p by del x is greater than 0. When del p by del x is greater than 0, so pressure gradients becomes positive. Once the pressure gradient is positive, so here the pressure was acting to accelerate the flow. So, when the pressure gradient will be positive, in this process the pressure will act to decelerate the flow. It will decelerate the flow, and once it decelerates the flow, what will happen, because viscosity is again, there is a viscous force which is always acting on the body, and that is decelerating the flow, and again this is also pressure is also acting on it, and this will also decelerate the flow, and as a result what will happen, the viscous force and the boundary layer thickness. So, the pressure, so since there are two forces which is decelerating the flow, so in the process the boundary layer thickness increases, very rapidly, and the flow soon reverses. So, in the process what happens when it in the process the flow del u by del y near the wall becomes negative. That means the flow decelerate and moves in the speed, the flow decelerate, and in the process what happen, there is a point at which the direction of the flow will come to a stagnation point. That means there will not be any flow and flow separation will occur. So, there will be a point when del u by del y becomes 0, and in the process there will be the flow separation will takes place. And after the flow separation, what happened? After this, if further it decelerates, the fluid will flow in the opposite direction. And in the process, and there the pressure gradients again, because will change the direction from positive to negative. And in this, here what happened, the boundary layer theory, this will able to determine the point of flow separation. On the other hand, it will not able to tell the flow pattern of flow characteristics. It talks about the point of flow separation. It will predict the point of flow separation, but unable to analyze flow past this point, analyze the flow past this point, past the separation point. This is one of the very major important point of the boundary layer theory. The boundary layer theory only talks about the point of flow separation it can identify, but it will not able to talk about the flow pattern at the separation point. There are several, there is another thing. So, already we have talked a lot about the laminar boundary layer theory and theory. Again, this laminar boundary layer theory holds when just the fluid becomes viscous just adjacent to a wall boundary, and beyond the wall boundary the flow is envisaged. On the other hand, we have also talked about laminar flow for unidirectional flows, intermediate Reynolds number, but in case of very large Reynolds number, laminar boundary layer theory holds good only for a class of problem. And again, beyond when RE, the Reynolds number RE extremely large, becomes large, much larger, and this boundary layer theory, results of boundary layer theory will not hold good, then the flow become turbulent, and in this region the motion, once the motion is turbulent, it is very difficult to predict the pattern of the flow, and the flow becomes random and it becomes very irregular, and the methods which we are using to analyze the, it becomes very difficult to analyze the flow. The classical methods in many situations fails. However, some of the methods like momentum integral equation methods can be applied, but the theory that is developed to deal with the boundary layer equation will no more hold, and it has to go for a, the theory has to be again looked into the flow pattern and other things. There are various types of equations which will be again derived from the Navier-Stokes equation, and so in that situations we are not going to those details of the theory of the turbulent flows, but we just stop here about this laminar flows boundary layer theory, and turbulent flow theory will not talk about in this series of lectures in marine hydrodynamics, because that itself will lead to a different type of analysis, and we are not going to detail. However, before concluding, I will just talk flow around a body. With this, I will conclude my lecture. Flow around a body. What happens when a body moves through a fluid, or when a body fluid flows past a body? Either a body is moving or the fluid is moving in a body. Fluid is moving, body is fixed. So, there are two types of resistance that appears. One of the resistance is encountered, the body encounters one type of resistance, the other kind of type of resistance is the fluid encounters resistance. There is a body encountered resistance, the other is a fluid encounters some kind of resistance. For example, when an airplane flying in the sky, particularly in the atmosphere, or a submarine that moves through water, the propulsion system has to exert a force that is should be sufficient enough to balance the forces like the drag forces, that is called the one of the force that is called the drag force. And for on the other hand, for a body immersed in a fluid stream, the drag force depends again on the shape of the body and orientation of the body, shape and orientation of the body. The drag force is due to, and this drag force is due to again due to the boundary layer. Drag force is due to the boundary layer. Boundary layers due to flow separation and wake. Then what is wake? So, there are several types. When this is the drag force is due to the boundary layers, flow separation and wake. Then another thing is here, there are several types of drag. Types of drag force on finally experienced by the body. Some of them are shear drag, one is a pressure drag and one is called wave drag. So, there are three types of drag basically faced by a body when it is immersed in the in water or in any fluid, and when the flow takes place with the separation. When there is a flow separation, what happens? It gives rise, when flow separation occurs, it gives rise to a zone of negative low pressure. It gives rise to a region of zone of low pressure, and in the low pressure this region, this zone of low pressure is called the wake zone. Wake zone. Just after separation, flow separation occurs, this wake zone is developed. Then the flow in the wake zone is highly turbulent. In this zone, the flow is turbulent. It is very difficult. The laminar flow theory or the viscous flow, the flow is turbulent and it is very difficult to analyze by using the classical boundary layer theory. And again, what happened here as a result, because there is a flow becomes turbulent. So, in the process energy dissipation takes place at a higher rate with a reduction in pressure. So, the pressure reduces after this. So, as I said, there is a low pressure region and pressure reduces. But so, what happened in the process, in the initially the body there is a difference of pressure is developed around the body, because initially the pressure was high and on one side, when the one side of the body on the front side and on the back side difference of pressure is developed, and this difference of pressure leads to the pressure drag. So, the front side of the pressure becomes higher than the back side of the pressure, and that is a result. So, this force arising arising due to this pressure difference is called the basically the pressure drag. Then and again this pressure drag again depends on the nature of the structure or shape of the structure, basically depends on the form of the body. Then on another aspect of this, what I say that wave drag, what again happen in this case? if you look into, particularly this happens in case of a ship, when a body like a ship which moves partially in the water and it is open, partially is immersed in the water. So, there are two types of waves, two types of motion produced, two types of waves, that is one wave is produced at the front. So, one is at the bow of the ship, and near at the bow there is a type of wave that is produced, and another wave is produced at the stern of the ship. This two types of wave, and these waves, one wave produced at the bow, the other wave produced at the stern, and this wave provides a resistance, they provides resistance to the motion of the ship. Motion of the ship, and this kind of forces, these forces are called the wave drag. So, the details about the various kind of forces acting on a ship, particularly drag forces and resistance forces, will not go to the details, just I have given you a brief introduction how these things happen, and the details will be covered in the course called resistance and propulsions. Which is normally taught in the, basically these kind of courses are taught to students of hydrodynamics, ocean engineering, or in the aerodynamics students, those who in the department of aerospace engineering. Hence, the understanding. So, what we understood here. So, the point of talking about this flow around a body is that there are so many kinds of we have to look into wave forces, we have to look into the pressure forces that is acting, various types of resistance, and again the boundary layer, the flow separation, the boundary layer, the wake formation, and again the viscosity characteristics as well as the irrotational motion characteristics of the fluid. So, this example itself gives us a background that the importance of this course of marine hydrodynamics, because in this course we are able to deal with the problems of large class of problems associated, whether it is a motion of a ship or a submarine, or any other ocean related vehicles, or even if structures, we can always know what are the forces that is acting on this. Again we have talked about wave forces in detail, and wave characteristics, we have understood various wave characteristics. So, all this will give us a good understanding, basic understanding about the various aspect of marine hydrodynamics, various aspect of the marine fluid in the marine environment, basically the subject what we call the marine hydrodynamics. So, here we have covered potential flow, we have also introduced to the potential fluid or other potential flow, then we talked about viscous force, viscous flow, then we have introduced to boundary layer theory. The important part, all these are taught in a very scattered manner, but finally the part which is more important to particularly to students of ocean engineering, naval architecture, is the wave part, water wave part. And in this way, this potential flow, though there is a commonality for a class of students of aerospace and engineering, and but major part of this, I did not spend much time on the viscous flow as well as on the boundary layer theory, because these courses that in detail various flow problems which are being taught to students of various engineering departments, particularly in physical sciences. So, the theory can be borrowed from there when it requires, but I have spent more time on the potential flow theory as well as on waves. In fact, we have taken almost 32 lectures on this potential flow and the wave problems, whereas we have just introduced in 8 lectures, around 7 or 8 lectures about viscous flow boundary layer theory. Another important point here I would like to highlight is that this drag reduction, particularly when it comes to design of ships or submarines, or any ocean related vehicles, we always consider the body as a streamlined body. And the idea is that because there are so many drag force act on the body, one of the main objective of this particularly for the designer is to reduce the drag on the structure. So, the body when the design, when they look into the design of the structure, the streamlined body, one of the basic objective of the design is to ensure that we are minimizing the drag that is on the body. So, that we will have less resistances and the less drag force that will be acting on the structure, and in the process the ocean going vehicles will be moves without fuel consumption and other design related life and life of the vehicle, or even if rather robustness of the structure will be there, and it will be one of the best better design and better engineering application. The most of the structures which are ocean going, or even if in air structures which are airborne vehicles, they are one of the main thing is that we always look into streamlined body, and these streamlined body are such that will help us in reducing the drag. With this understanding and with this much details, I will stop here on this course. This is the last class, and if there will be a need, I will again take few classes, but for timing we will stop here. Thank you.